So we're going to finish this discussion of the chemical bond. Focus on covalent bonds. So here's the problem with the valence bond theory, localized electron model. And we've already encountered some problems with it. For instance, when we had to deal with equivalent, or not equivalent, but multiple valid Lewis dot structures for any given compound. And the way we dealt with that was resonance. Right? For resonance was that was a cheap fix. Here's another one. When we write the Lewis structure for methane, right, we're going to have 4 plus 4 electrons, 8 electrons. All right, so we know at this point that we're going to have, right, that Lewis structure, and there are no leftover electrons, right, 2, 4, 6, 8. And the VSEPR model says that this is a tetrahedron. Right? So we will have carbon in the middle, and then we'll have a hydrogen here, one over here, and one in the back. Right, to give us this trigonal base and a regular structure. And all the bonds, every one of these bonds is 109.5 degrees. Okay, here's the problem. Right, the shape is tetrahedral, the bond angle is 109.5. Here's the problem. If the valence bond theory is correct, and electrons belong to individual atoms and they only share them to make bonds, then we know that the hydrogen electron comes from the 1s orbital. I mean, we have no other choice. Right? We have hydrogen with 1s1. That's its electronic configuration, and it donates that electron to this bond. So the other electron for the bond has to come from the carbon. So let's look at the carbon. Let's see. We'll do the whole thing. Right. So it's got 1s2, 2s2, 2p2. Right. Okay. These are the valence electrons. So these are really the only ones that we're focused on. Just the principal quantum number 2. The s orbitals are spherical. Right. So those electrons, those 2 electrons are in the spherical s orbital. The p electrons are dumbbells. Right. So we could have 1 electron here and 1 electron there in the p orbitals. Okay. Here's the problem. If you're going to have equally spaced hydrogen atoms in this molecule bonded to the carbon, then 2 of them are going to be this type of bond, and the other 2 are going to be this type of bond. There's no way that you can get a regular spacing of those hydrogen carbon bonds with 2 different ones from carbon. Okay, so that's another fly in the ointment. We can't overlap properly to give you this structure, and this is confirmed experimentally. This is the structure of methane. So how do we deal with it? We need a fix, right? And the fix is hybridization. We hybridize the bonds so that we get, instead of these 2 and with this one and these two, we get an equivalent hybrid bond. So we're going to take, and this is just one orbital here. So this is the one orbital for the S. And then how many P's do we have? Well, we have 3 P's, right? We have 3 available P orbitals, 1 S orbital. And if we hybridize that orbital, now we have 4 equivalent sp3 hybrid orbitals. That's the way we get around it. And we're still able to say that these orbitals are localized to the carbon atom. This fix was proposed by Linus Pauling in 1931. All right, that just restates the problem there. And that gives the fix. So, in order to, since we're dealing with a quantum mechanical model for the atoms, and we extend that into a quantum model for the valence bond theory, then it has to be mathematically supported, right? So in order to get the hybrids to work, the quantum mechanical model for the atom has to be modified. So it gives you these hybrid orbitals. That's way beyond my pay grade. But I'm sure Pauling had to do it. Or he had to call up one of his buddies who was well versed in the mathematics and could, be a co-author. Okay. So these hybridized orbitals only form when they're needed, right? Otherwise, the atom is going to be like this. But when it gets into a bonding situation and it needs 4 equivalent orbitals like this tetrahedral structure, then it will hybridize into an sp3 hybrid orbital, and there will be 4 of them. So what you may have already noticed is that when you put 1 of these and 3 of these together, you have to get 4 of those. Right? The number of orbitals going in must be conserved in the number of hybrids coming out. Now, as far as the energy goes, we know that the p orbitals are slightly higher energy than the s orbitals. But when we hybridize them, we get something in between. We get energy levels that are lower than the p's and higher than the s's. And it's roughly 25-75% split, because 3/4 of them are p character contributors and 1/4 are s character contributors. So that's where you get 25 versus 75%. That's why the sp3 energy level is closer to the p's. There's more p character to the sp3 than there is to other hybrids that we're going to discuss. And this is what the mathematics, the quantum mechanical mathematics predicts is the probability distribution for the orbitals. Right? We put these 4, the 1s and the 3 p's together, and we get those 4 equivalents. And you can see that the way they're structured, they're pointing to points of a tetrahedron. And as always, these are probabilities, right? The electrons could be other places. The only place that we're sure that they're not is at a node. If we identify a node, then there won't be any electrons there. But the rest of it is like a 95% probability that they'll be in that space. And there's always that 5% probability that they won't be. Okay, so this is what the methane molecule would look like in a space filling model. And the hydrogens don't have to hybridize. The overlap here is between this s orbital and one of these sp3s. Okay, so how about something like ammonia? It only has 3 hydrogens. So should we assume that we only need to hybridize 3 of the p orbitals? Well, do not steal my own thunder. Okay, so we are going to describe the bonding in the ammonia molecule. First thing you do is draw the Lewis structure. Okay. So we've got 5 and 3, which is 8 electrons. And we're going to have N like that, like that, like that. We have 6 used up in bonds. That means nitrogen gets 2 more, lone paired. Okay, so the electronic structure is tetrahedral. And the molecular structure, we found before that that's going to be a trigonal pyramid. Right? And if we draw it in the best way we can, right? That hydrogen in the back, these hydrogens out here, giving us this trigonal base. So the tetrahedral electronic structure is in here, and the trigonal pyramid is the molecules, the atoms only. All right, so we got our Lewis structure drawn, and we've determined, based upon the VSEPR model, what our electronic and our molecular structure is going to be. So what hybrid orbitals are necessary to take care of these 5 electrons that come from, let's see, well, it's going to be a 7, but 5 of them are valence. So we got 1 here, 1 here, 1 here, and 2 there. So that's 5 of those. 1 goes this way, 1 goes that way, 1 goes that way. If this electronic structure has to be tetrahedral, and it does in order to give us this molecular trigonal pyramid, right? That's experimental evidence proves that. Then we've got to include these lone pairs in the hybridization. So nitrogen is also going to have sp3 hybridization with 1 lone pair in a hybrid orbital. Okay, so that's what it looks like there. And then well, I didn't draw out the this is going to be 1s2, 2s2, 2p3, 2p3, because there's 5 of them. 3, 4, 5, 6, 7. Yep. So we're going to hybridize these orbitals, and that will give us our sp3 hybridization and agree with the experimental evidence. Okay, so there's what it would look like. Now the we've already talked about the difference in the bond angles here. Bond angles are going to be less than 109.5. I don't remember what it was, 105, something like that. That's because this lone pair is not confined in a bond, so it kind of balloons. And the ballooning puts pressure on these bonds, and that decreases their angle. But the hybridization is sp3 tetrahedral. And notice that with tetrahedral, we need 4 groups, right? VSEPR says 4 groups will give us tetrahedral. So we have to have, we have to have 4 hybrid orbitals in order to satisfy that condition. Ooh. All right. How about a more complicated molecule like ethylene? C2H4. Okay. So if we're going to draw this one, we need 4 valence electrons here would be 8, and then 4 more would be 12 electrons. Okay. So carbon, we can't bind 2 hydrogens together and then something else. So the only way we can go is 2 carbons like that. And then to balance it, we're going to put 2 hydrogens on each carbon. Okay. What does that mean? That means we have 2 central atoms. So for this one, what's the structure going to be? 1, 2, 3. So 3 groups means what to VSEPR? It means trigonal planar. Right? So it's trigonal planar around that carbon, it's trigonal planar around that carbon. Okay. All right. So if it's trigonal planar, all we need is 3 hybrid orbitals. Right? And we know the bond angle is going to be 120 degrees, right? For trigonal planar. So we only need 3 hybrid orbitals, so we're going to use S and then only 2 of these. Okay. Now, the carbons have the same setup as before, 1s2, 2s2, 2p2. And there's 1 of these and 3 of those, 3 p's. But since we only need 2 of these p's, that means we're going to have 1 of the s's, 2 of the p's, and 1 p is left out. It stays a p with its geometry. So we get an sp2 hybrid here to satisfy this condition, and then the extra p orbital. Let's see. We have 12 electrons. Yeah, 12 electrons. We only have, let's see, 1, 2, 1, 2, 3 from that carbon, and then 1, 2, 3 from this one. So 3 from this carbon, 1, 2, 3 from the others. That means we have 6 electrons that are in the bonds so far. I'm not finished yet. So do we have enough orbitals here? Well, yeah, right? We can put 2 orbitals in each one. We've only used the X and the Y's for this one. The Z is over here. So we've got 2, 4, 6. We've got room for 6 electrons. Okay. So what's over here? If we've used up 6 electrons in this side, let's see. Well, if the orbital's full, we got 6 electrons. We got 12 total. And we got 4 coming from each one. 2 times 4. All right. Okay. So for each carbon, we've only used up 4 of these valence electrons. Well, there are 4 there. That's total. One, two, three. Oh, we're only using 3 electrons for each of the carbons. So 2 times 3 equals 6. We've only used up 6 electrons. That means we have 2 more electrons left over. We've got 1 here and 1 here that hadn't been used. So those 2 go into another bond. And that's where this orbital comes in. So if the sp2 hybrid orbitals go here, and one of them is here, like sp2, sp2, for these carbons. So this has 3, it has 3 here and 3 here with an overlap there. Then this one is an overlap of p orbitals, the pz's for each carbon. Okay, let's see if we can pull up some pictures that will help look better. Bond angles, okay, so we knew that from the last chapter. Oh, and we've done this before, haven't we? Where we have, I'll just redraw it. If we're using the VSEPR model, then we have 2, 4, 6, 8, 10. We've got 2 more electrons, 1 here and 1 here. Then we have to make an octet, so we do that. So 2, 4, 6, 8, 2, 4, 6, 8. We did that last chapter. What I'm trying to show is how do we get to that place with hybrid orbitals? All right, so we've got a hybrid orbital here, here, and here. We got 3 sp2s, 3 sp2s for this carbon, 3 sp2s for that carbon, and then we have a pz for each. And that's where we get the double bond. These are all on axis. They're sigma bonds. I think we get to that in the next couple of slides. Right, okay. This is asking a rhetorical question, actually. Why can't sp3 hybridization account for the ethylene molecule? Because the bonds are not 109.5 degrees. It's not tetrahedral structure. It's trigonal planar. So sp3 would be the wrong hybridization. sp2 is the correct hybridization to give you that 120 degree bond angle. And yeah, here it is. So anytime the bond is on axis between these carbons, say, this would be a sigma bond. This is an overlap of the sp2 hybridized orbitals. And then the other 2 go to the hydrogens. Okay. So the other 2 go out here to the hydrogens. And then you've got this unused p orbital. And we get overlap there. So that forms a pi bond. The sigma bonds are always on axis, and you always have to have a sigma bond. And you can only have one sigma bond because there's only one axis between the atoms. But if you get some sideways overlap, you can form a pi bond. The pi bond is more strained because the overlap has to occur off axis like that. Whereas on axis, there's no strain, right? But there is some strain on the pi's. And you can get a pi overlap this way, and you can get a pi overlap in the back or the front. So you can have one sigma bond, and then you can have 2 pi bonds. We only need one pi bond, so that's why it's the way it is with just a double bond. A sigma and a pi makes a double bond. Okay. So the energy for these orbitals, the 2pz, this one left over is at the same energy level as it was before, at that atomic energy level. But the sp2 hybridized orbital is at a lower energy, and it has 33% s character and 67% p character. Because it has fewer p orbitals in it, then it has more percentage s character. And that brings the energy level down lower. So this is what it would look like, artist rendition of the sp2 hybridized orbitals. You have three of them because you got one s and two p's going in. You have to have three hybrid orbitals. And then you have the one p orbital left over. And this is what the hybrid orbitals would look like. We already know what the p orbital is going to look like. These hybrid orbitals are spaced in such a way that they point toward the apexes of an isosceles triangle. If an atom is surrounded by three effective pairs, a set of sp2 hybrids is required. Right. So there we get overlap of the sp2 hybrids on axis gives you the sigma bond, and then you have one unused p orbital on each carbon that overlaps to give you the single pi bond. Okay, how about carbon dioxide? All right, so we got CO2. It's a valid molecule. We know it exists. This has 4 valence electrons, and 2 times 6 is 12. 12 valence electrons, 16 electrons. Okay, so far we know this much. Two, 4, 6. So we got 10 electrons left over. 2, 4, 6, 8, 10. No, wait a minute. Is that right? Well, 4, 16, that's right. 2, 4, 6, 10 electrons. 2, 4, 6, 8, 10. 10. That doesn't seem right. I must be drawing it wrong. Oh. Does anybody catch my mistake? I got an extra carbon in there, don't I? Okay. Now we're talking. 2, 4, 6, 8, 10, 12, 14, 16. Now we're good. Okay. Let's pick up where we left off. So around that carbon, we have 2 groups, right? 2 groups equals linear, right? So this has to be 180 degrees. Okay, got to make an octet around that carbon. So we found from calculating the formal charge, I think we did that last chapter. Formal charge tells us that a double on that side and a double on that side is the preferred structure. Okay, so now that we've got our preferred structure, we know it's linear. Then how do we hybridize this carbon so that we get 2 equivalent hybrid orbitals pointing in opposite directions? Well, we only need S and a P. If we put an S and a P together, then we have to have two of them. Because two went in, two comes out. Okay, so one SP goes this direction, the other SP goes that direction, and makes two sigma bonds. Okay, so what's left over? Well, if we only take the X to make this one, then we've got two P's. Actually, we have, let's say, we have a P Y and a PZ untouched around each carbon. So you can view them as this way, right? Or into the board like this. And that takes care of the carbon. How about the oxygens? Well, the oxygens, let's see. Oh, the oxygens may not have to hybridize. They have 6 valence electrons. Oxygen, well, oxygen has 8, so it's 1s2, 2s2, 2p4. So oxygen has its p orbitals, and they can overlap. It has 3 p's. It doesn't need to use the s's, so it only needs the p's: px, py, and pz. And it can take this hybrid orbital here, and you can get, right, the px's here from the oxygen to overlap these two sp hybrid orbitals this way. And that gives you a sigma on this side and sigma on that side. So what do we got left over here? Well, we've got a py and a pz on that carbon. I just drew those. This is py and this is pz. Well, oxygen also has a py and a pz. Getting kind of busy in here. So in the plane of the board, we can get this overlap here and this overlap. Let's see. Yeah, this overlap here will take care of a double bond on this side. And then these orbitals here, like that and like that, will take care of the double bond on the other side. I think I got a picture in here somewhere. Okay, the molecule is linear. There it goes. All right, so as far as the energy goes, the two unused p orbitals for the carbon will be at the same energy as the atomic orbitals, but the sp or hybrid orbital has 50% s character and 50% p character because there's only one each. And it looks like that. So it's going to have more S character. It's going to look more spherical. Okay, so here we go. We've got the sigma bonds in the middle. This is a better picture. Sigma bonds in the middle with the sp hybridized orbitals. And then we've got the in plane for one side of the carbon and the perpendicular to the plane on the other side of the carbon for the pi bonds. Pi bond on one side and the pi bond on the other side. And then the, wait a minute, oxygen is also hybridized. Okay. That's my mistake. Oxygen has to be hybridized. It needs, okay, around each oxygen, right, you've got this bond with the carbon. So what's left over? Well, we had right? On each side. Two, 4, 6, 8, 10, 12, 14, 16. So there are all the electrons. And we've got to have room for sigma overlap and pi overlap. So the sigma overlap, what we can do with this oxygen is we need room for these three. Okay, so what happens is you get sp2 hybridized orbitals, so you have three of those. And they form a trigonal planar electronic structure around this oxygen with one unused p orbital on either side. So within this sp2 hybridized, these sp2 hybridized orbitals, you get an overlap here. And then you have, right, this trigonal planar structure, and two of those lone pairs go into those orbitals. And then this one supplies for the pi orbital on either side. So the sp hybridization for sp2 hybridization for the oxygen supplies both a bonding orbital and two sp2 hybrid orbitals for the lone pairs. Let's see. They only showed us the carbons for this one and just assumed that you are going to accept that the oxygen was hybridized also. Well, the fact of the matter is, experimental evidence shows that that's what happens. You do get hybridization from the oxygens also. Only they are sp2 hybridized and the carbon is sp hybridized. There we go. Without all the clutter. All right. I'm going to build a chart in a minute that'll hopefully pull this all together. As long as I got time to do it. I only have to get halfway through this chapter today. Next Tuesday, we got time to finish it off. How about bonding in the N2 molecule? Okay. So if we've got two nitrogens with 7 each, actually 5 valence electrons, that's 10 electrons that are in the valence orbitals. So we would do this, and then that would take care of 2, and we need 8 more, right? 2, 4, 6. 2 times 5 is 10. Yeah. Together, that's 2 minus 2 is 8. 2, 4, 6, 8. Okay, so we're good there. All right. So what we would have done with the last chapter is we need to make an octet, right? So how do we do that? Well, 2, 4, 6. What if we bring 2 over there like that? Then we have 2, 4, 6, 8. 2, 4, 6 is still only 6 on this side. So we would take 2 more and make a triple bond. Okay, so we got 1 sigma and 2 pi's. Okay, how does the hybridization work for this one? Well, we only need that 1 bond. This is linear. So it's also, each one of these is going to be sp hybridized. Right, we put 1 s in, 1 p in, we get 2 of those. So we've got this sigma bond between these. And then we have left over a PY and a PZ. Let's see. PY and a PZ, this. And these overlap to give you one pi bond, and these overlap to give you the other. Okay. Okay. Linear arrangement, yes. SP hybridization. So apparently, anytime you have a linear molecule, then the central atom is SP hybridized. Because that's the only way you can get a 180-degree bond. Okay, so that's what it looks like with your SP hybridized bonds and your two unused p orbitals. All right. So far, let's see. Let's start over here. Electron groups. Right? So far, if we have two electron groups, and we know that we're going to need two hybrid orbitals that are sp2 hybridized. Okay, that gives us an electronic geometry of 180. Well, let's say linear, and angles 180 degrees. Okay. If we have three, we know that we need sp2 hybridized, right, for three of those orbitals. And this is going to be trigonoplanar with 120-degree bond angle. And then we started off with four groups with sp3 hybridization, and this is tetrahedral. I'm leaving out the molecular geometry because it just depends on how many lone pairs you have. And this is 109.5 degrees. Okay. So with PCl5 is our next example. Phosphorus is 5, and this is 7 times 5 is 35. So that's equal to 40 electrons. So if we put the P in the middle and do like we did before, and the chlorines are here, right? 2, 4, 6, 8, 10. That means we have 30 electrons left. And if we put 2, 4, 6 around 5 of these, that takes care of all the electrons. So we don't need any lone pair. We do exceed the octet, though. The chlorines have octets. The phosphorus exceeds the octet. Okay, so what's the structure here? Right, according to VSEPR, 5 groups is trigonal bipyramid. Okay, so if we draw in this triangle in the center, and then we have the opportunity for bond that way and that way, with phosphorus in the middle, and we have positions 1, 2, 3, 4, 5. All the positions are occupied by atoms in this molecule. Okay, so the bond angles can be either, if we go from here to here, that's 180 degrees. If we go from here to here, that's 90 degrees. And if we go from, say, here to here, that's 120 degrees. Okay. So the way we hybridize that phosphorus to accommodate those chlorines is we need 5 hybrid orbitals. We don't have any more P's. But phosphorus, notice phosphorus is in the third period. It has access to d orbitals. So dsp3 hybridization will give us that structure. Okay. Trigonal bipyramid, 9100, 180, yes. So we have 5 equivalent hybrid orbitals that can accommodate all those chlorines. And obviously the chlorines are not hybridized at all. Okay, how about this one? And this is as far as we're going with the hybrids. We're not going to go any further in this course. Xenon tetrafluoride. Okay, this has 8 valence electrons, and this has 7 times 4. Okay. So that's 28, 36 electrons. Okay, so we would have we'd start off like this. 2, 4, 6, 8 would be 28, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that's 4 electrons left over. There and there. Okay. So if we have 6 groups around the central atom, the electronic structure would be octahedral. So we would draw our little square in the middle. That's where xenon would sit. And then we would have those positions occupied. Well, for octahedral, if there are any lone pairs, octahedral puts them at the apexes, and the fluorines go on the square. Okay. So this is going to be octahedral electronic. And with these, the only bond angle you can have here is 90 degrees. But if we have these occupied with atoms, you would also have these 90 degrees, but you'd have 180. So maximum of 180 degrees if we have atoms to occupy those positions. That's only, not for this molecule, but for other molecules. All right, so how do we get hybrids for that? Well, we got plenty of Ds, so we just use 2 Ds. Okay. How many Ds do we have? We've got 1 S, we have 3 Ps, and 5 Ds available. So we only have to use 2 of them. So that tells me that we could go up to 7, 8, 9. Let's see. 7, 8, 9, and we'd still be able to use up the Ds. But we're not going there. That's too much for this course. Okay. So octahedral. So actually, this is the electronic structure, right? This is going to be square planar as a molecule. But the only possible bond angles are 90 degrees. Okay, 2 Ds, 1 S, and 3 Ps. Gives us 6 equivalent orbitals. Right, that's a good point. We know that since this molecule is square planar, experimental data says it's square planar, that means those four can't be arranged in a tetrahedron, not like methane, right? They're square planar. That means we have to provide a location for the lone pairs in the hybrid scheme. If we don't, right, if these lone pairs are not put in the hybrid scheme, then these four have to go into a tetrahedron. Right? And they can't do that because experimental evidence says they're square planar. So we have to include those two lone pairs in this D2sp3 hybridization. And the hybrid orbitals would have to not only bond with the fluorines, but provide locations for those lone pairs. Okay, so here's the hybridization. Octahedral electronic structure, D2sp3 hybrids. Oh, there's a chart. Okay. So you get it in two locations. And you'll notice that whenever you have two groups required, it's sp hybridized. 3 is sp2. I mean, there's a correlation between the numbers here and the numbers required here. So 1 plus 3 is 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So it makes it easier deciding what the hybridization is. How about hydrogen cyanide? Well, that was given out on me. Okay, we have 1 here, 4 there, and 5 there, so that's 10 electrons. It would be like this, that, 2, 4, 6 left over. We start from the outside and work our way in, 2, 4, 6. Okay. Now we know that we've got to make an octet with this carbon, so we're going to take these two and make bonds out of them. So before the chapter we're in now, we knew that this was going to be a linear molecule. Okay. So linear requires sp hybridized. This one is going to be sp hybridized. This one has a bond in here and a lone pair out that way. So it's also going to be sp hybridized. Okay. So that leaves this sp hybridized takes care of the sigma bonds. Okay. And then we're going to have unused, we're going to have 2 unused p orbitals here that can overlap to give you the other pi bonds. All right, there's a sigma and there's a sigma. Remember, you can't have pi's until you have at least 1 sigma. Well, actually, you have only 1 sigma. No other possibilities. Then you can add the pi bonds in. All right. Got a few minutes left. We could try some of these. Let me see. Let me see how much room I got to go. Okay. I think we can make it. We did ammonia and carbon dioxide already. Right? So let's go on to sulfur dioxide. Okay. Sulfur is going to have 6 and oxygen is going to have 6, so that's 18 electrons. Let's put the rest of them up here. Cl5. So there's 6 halogens. 6 times 7 is 42. Right? And then krypton tetrafluoride, probably going to be like xenon. But we've got 14 and 8 is 22, right? Oh, that's 2, excuse me. That's only 2. All right. So this is going to say sulfur's in the middle. We have oxygen, that's -4. We have 14 left over. 2, 4, 6, 8, 10, 12, 14. So around the central atom, and we're focusing on the central atom. That's the problem. So the central atom has 3 groups, which means trigonal planar electronic geometry. That means we need 1, 2, 3 hybridized orbitals, sp2. Okay. Let's see. We already did the ammonia, and the bonds would be 120 degrees. 120-degree bond angle. Okay, SO2, sp2 hybridized, 120. Okay, there you go. Oh, they're not doing them in the order that I wanted to. So let's go back. Let's go with this one then. This is the next one in our that showed in our animation. So here we have 14 and 8 over 22. I already did that. All right, so we have like that, fluorine. So that's -4, which is 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. 1, 2, 3, 4, 5 groups. 5 groups means trigonal bipyramid. And that's D2sp3. No, D1sp. 1, 2, 5. There we go. DSP3 hybridization. So that means that we have possibility for angles of 120 degrees. Well, actually, where do the lone pairs go in a trigonal bipyramid on the triangle? We've got 3 lone pairs that need to go on the triangle. That means these are going to be opposite each other, right? On that structure. So they're only 180 degrees apart. That's it. That's all you can do for bond angles. It didn't mention polarity. I just added that for extra. Okay, how about this one? I think CO2, we've already done that one. 180 sp hybridized. And then ICL5. Okay, so we're going to have this in the middle. 1, 2, 3, 4, 5 fluorines. We already do this one. Something else in the middle, wasn't it? But that gives us 2, 4, 6, 8, 10. That means 32. And 2, 4, 6 times 5 is 30. So that's 2 electrons left over. So we got 1, 2, 3, 4, 5, 6 groups, which is octahedral electronic geometry. That means with 6 groups, we have D2sp3 hybridized. And that lone pair in an octahedral group is going to be on an apex. So we're not going to have any 180-degree bond angles for this one, because opposite one of these chlorines is a lone pair. So what we have is square this way and square that way. It's only 90 degrees. That's all we got left. Yep. Okay. All right. So this is just a summary of what you do. You go through the procedure of go all the way through VSEPR and get your electronic structure. And that'll tell you how many groups you have to deal with the hybridization. And then you count up the number of groups, and then you construct your hybrid orbitals to give you the right number of hybrid orbitals. All right. So this is setting us up for the next half of the chapter. What's wrong with the localized electron model? Well, the first thing is the assumption that electrons are localized. That requires, in some cases, resonance to be added, and in other cases, hybridization to be added. It does not deal effectively with unpaired electrons, free radicals. We put them in there and count them as a group, but it's not really the case. Like our, what was it, nitrate polyatomic ion, or was it NO2? One of those had a free radical in it. It doesn't provide any information about bond energies. You cannot calculate bond energies from this model. We can't even semi-quantitate them. We can say, okay, qualitatively, it's going to be more like a p orbital, higher energy than an s orbital if it has sp3 or sp2 hybridization. That's as far as you can go. There's no way. The model does not have built into it a way to calculate bond energies and put numbers on them. So that's where this is a good place to stop, because next we'll get into molecular orbital models. We've been working through, historically speaking, the progression of understanding of what a bond is. And we've made it through the valence bond theory with its localized electron model and the VSEPR model. And they're still good under certain circumstances. I mean, they agree with these experimental results up to a point. But those shortcomings that I just mentioned are tackled with the molecular orbital model. And that's the more recent model. It's also quantum mechanical, right? It's got all of its equations to go into and predict the structures, but it also tells you something about bond energies, values for bond energies. But it requires a major shift in what we think the electrons are doing in the bonded environment. That's going to change radically in order to provide this much information. So we'll pick that up next Tuesday.